Good morning. Dear audience, on behalf of the High Voltage Laboratory of TU Delft, we want to take this opportunity to share with all of you the main results of an alternative partial discharge measuring technique for high voltage DC GIS based on magnetic detection. The measurements of partial discharges are used worldwide by manufacturers and utilities for the detection of defects as an important tool for the monitoring and diagnostics of high voltage GIS. But also they are used to understand the dielectric properties of alternative gases that will soon replace SF6, especially in future DC GIS applications. Conventionally, PD measurements on GIS have relied on several broadband techniques to detect the electromagnetic waves produced by a PD event, for example, using capacitive couplers. For this, standards as the IEC 62478 advise on the setups and working frequency ranges, while other documents, such as the SIGRE Working Group D125, defines a sensitivity check procedure to verify that a UHF measuring system in field can pick up signals equivalent to 5 picocoulombs as measured by the conventional standard IEC method during laboratory tests. To present, the UHF method are the standard for AC GIS and are being migrated to DC GIS installations. They indeed have gained popularity because of their high local sensitivity and noise rejection. However, the PD signals in the UHF range are heavily attenuated with distance, pressing to install UHF couplers every few meters. The intrinsic nature of the UHF detection and the attenuation also make it impossible to quantify PD parameters, such as the apparent charge. TU Delft, in Working Package 15, has been researching complementary PD detection techniques that can mitigate the limitations of the reduced spatial sensitivity and PD parameter quantification of the traditional UHF methods. A technique based on magnetic detection of PD signals in the low frequency range, as compared to the UHF range, has been proposed and reported in D15.3 and D15.5 within Working Package 15. This alternative technique relies on the concept that in the TEM propagation mode, PD currents flow along the GIS, compartments, and main conductor as in a transmission line. If so, then such currents can be picked up by magnetic sensors. We experimentally demonstrated this by inserting high-frequency current transformers in the path of the current from one compartment to the other. As can be seen in the graph, the outputs of the HFCTs overlapped each other. This is a remarkable finding because it proves that the PD current is evenly distributed in the compartment perimeter. Therefore, a certain input current can be correlated to the output of a magnetic sensor placed in the GIS compartments. To prove this hypothesis, we developed a magnetic sensor comprising of two single and independent loops, forming a half cycle in a mirror-like arrangement. The magnetic antenna is then inserted in the same openings where the UHF couplers are conventionally installed. This is an important point because it implies that not extra modifications to the GIS design are required. Finally, a signal decoupling capacitor and an amplifier is connected to the output of the antenna and then to the oscilloscope for time domain acquisition. Magnetic detection is convenient because the polarity of the output signal can be used for discrimination of PD signals from disturbances. When the PD current passes one compartment opening, the magnetic flux links each loop in a different direction. As a result, the polarity of the top loop is opposed to that of the bottom loop. In addition, providing sufficient noise rejection and amplification of the output signal, the antenna can measure with enough bandwidth as to reasonably estimate the charge of the PD pulse. Both an actual size GIS and a calibration rig were used to research the limits of the charge estimation. The underlying reasoning of the experiments was to inject a calibration pulse from which a reference charge is calculated and to process mathematically the output signal of the antenna to ultimately seek the relationship in equation 1. The results showed that the scatter is low, therefore a calibration factor is feasible. Further experiments were carried out, this time using HVDC GIS in Arnhem. A set of 3 magnetic antennas were installed in different locations, together with an FX6 Corona test cell at one end of the GIS loop. A broadband HFCT just next to the test cell measures the source PD current from which the reference charge is estimated. In this setup, there are many more parts and components between the PD source and the antennas. This allowed to test the influence of the attenuation and distortion of the signal in the charge estimation. After synchronously recording 1000 PD signals using the HFCT as the trigger of the oscilloscope, it was obtained that around 50% of the total signals had an error of around 10%, and 80% of the signals an error up to 20%. These figures are remarkable, especially having in mind that the absolute value of the reference charge was around 17 picocoulombs at the test cell. The splitting of the PD signal at the injection point implies that the signal reaching the antennas is at most half of the signal at the source, and this can be an indicator of the high sensitivity of the antennas. On the other hand, the scatter of the estimation was low enough as to render the estimation of a calibration factor feasible, using a laboratory calibration rig or an actual size GIS. The results also highlighted the lower attenuation of the PD signal in the low frequency range where the magnetic antenna works. From the graphs, it can be observed that the antennas at position 1 and 3 had almost the same amplitude despite of the very different propagation path of the signals. At position 2, the amplitude of the signal in fact decreased to half. Although the charge estimation from this antenna might have a higher error, his peak amplitude still makes it possible the PD detection. During promotion project, we have researched a new and complementary PD measuring technique. To summarize 2 Delft contributions to Working Package 15, we can mention that the charge estimation in GIS was proven feasible. The GIS parts have a moderate impact on the error of the charge estimation. Despite the limitations in charge estimation, the sensitivity of the magnetic antenna is good for PD detection. As shown in this presentation, extensive laboratory experiments have led to promising results that are steering the research line of our group for the coming years. Future works will focus on tackle the influence of background noise and the reduction of the hardware and data post-processing requirements. Thank you for your attention. For further questions, don't hesitate to contact us.